All right. Hello, everyone. There we go. Hello, hello. Welcome to another COMP6991 lecture. In fact, welcome to our final COMP6991 lecture before Flexibility Week. Don't worry, not our final COMP6991 lecture in its entirety. Yeah, it's going to be our last little lecture here before we get a week's break. Well, a week's flexibility, I suppose you would call it. Yeah, we're continuing on where we left off on Monday, and very exciting. A new house again. Fortunately I didn't have to go. I didn't have to change houses since Monday once again, but I have done away with the green screen because I don't know, the background's nice enough and the green screen's annoying. So yeah, screw the green screen. If my camera ends up blocking something, then let me know. I suppose I'll be spending probably a lot of time in a terminal, so I might just go ahead and make a little thing right now that I think about it, that sort of reminds me, if I can't see it, then they can't see it. There you go. Now there's a terminal in my corner, so like I won't be being like, why can't anyone see this, because there's a bloody terminal in the way. Cool. I see that everyone's very excited to get Morphin. Polymorphin Power Rangers. Yes. Cool. So a couple things, as usual, before we get started. I believe since the Monday lecture, I think it wasn't fixed before the Monday lecture. The submissions for the what was it called? The modularity exercise has been like fixed in quotation marks. It is like a fix. You can now submit for the exercise, but it's just like a kind of not the best solution-ish. Hence why I put it in double quotes, but you can submit the exercise. I also extended the deadline by a day just to give everyone a chance to make sure they submit it. So all the other exercises for week 4 are due tonight. I believe our usual deadline is 9 p.m. But the modularity exercise, I've thrown another 24 hours on that for everyone just to get those submissions in. So yeah, to compress your tar. That seems like maybe you need to clean. You need to run like a cargo clean before you before you tar it up. I put it in I had to change the submissions instructions once after I sort of put the instructions up because I forgot to tell people to clean, because then you're sort of submitting all your build artifacts and potentially dependencies and all that, which can take up a lot of space. I will try and make sure if anyone did end up compressing their tars, it's a manually marked exercise, so I think it'll be pretty obvious to a marker if like, oh, this doesn't look like if this doesn't look like actual code if it was compressed. So I'll put something in to check for it. But ideally you run cargo clean before you submit, and then you shouldn't, like, you get, I think something like you get like 8 megabytes or something like that, or maybe it's like 4 megabytes or something like that, which should, for a small text file, should be more than enough. So you probably submitted something that you didn't you didn't intend to. And yeah, you need to submit as crate.tar. Yeah, which is sort of why it's a little potentially strange x-zipping it if the extension isn't there, but I'll try and make sure we account for that regardless. Favorite part of the lecture is when Zach said it's polymorph time and polymorphed all over Ferris. Very good. And just renamed it. Yeah. Okay, cool. So there's that. The submissions are fixed. Make sure you submit modularity. And the other important one was so I addressed feedback a few lectures ago, or 2 or 3 weeks ago, and then I was like, oh, we'll do it on the Monday, and then the Monday lecture got cancelled, and so then I was like, oh, okay, well, not the Wednesday, and then this Monday rolled around, and I was like, damn it, this is a really busy week. I don't want to we're doing a lot with generic type parameters and traits and all that. So I don't want to lose a bunch of lecture time because there's a big chunk of feedback. And so I thought I'd just quickly take a thing here to say we're going to address that big chunk of feedback in like a forum post or something, as opposed to the lectures now, just so we can make the most of the time we've got. But you can keep your eyes out for a forum post if you've submitted feedback or you're interested in hearing on like how we address it or any plans we make or anything like that. But just thought I'd let you know it's not being we're not just like ignoring it and not planning to deal with it or address it. We are planning to address it, but we've just had like, oh, we'll do it in lectures. Actually, no, we won't. Oh, the lecture got cancelled. Oh, this is busy. And so we've got a big Google sheet. Tom's very nicely gone through and like labeled everything and organized it all. It's very nice of him. And we're going to put together a forum post at some point that talks about that. The usual reminder, yes, again, this is Wednesday, week 5, which means we don't have lectures next week. We don't have workshops next week. And you won't have weekly exercises next week. I don't recall what we set the due date for the week 5 exercises to be. So, okay, the week 5 exercises are still due week 6 Wednesday, which is illegal. Not allowed things due in flexibility week. Technically, you are allowed regularly scheduled activities to be due in flexibility week, assuming you also have a reasonable amount of time outside of flexibility week as well to do that. That's why the intro courses and stuff still have weekly tests and stuff like that often. But Shrey mentions now it's a mistake on his end, and we're going to update this to be week 7. So you won't have this. Don't worry about this deadline yet. I suppose we'll update it sometime soon. There you go. I justified it both ways. How about that? Cool. And as a reminder, your assignment 1 is due. Did I miss it? Here. Week 7 Wednesday. At 5 p.m. Is our usual deadline 5 p.m. or 9 p.m.? 9 p.m. Should probably be 9 p.m. as well. Maybe we're having a bit of a deadline headache. But anyway, so they'll both probably be due. Well, this is due week 7 Wednesday. The assignment, that is, and the exercises will get their due date updated to also be week 7. Cool. And the week 4 exercises again due today at 9 p.m. apart from modularity, which you've now got an extra 24 hours on. Cool. So yeah, in theory, Labo 5 is probably going to be due the same day as the assignment, I would imagine. I'm not sure if we're going to stick to 5 p.m., 9 p.m. It may not warrant a whole announcement on its own if we just change the deadline by a couple hours for consistency, but I'll probably just put like a thing on the forum, like a just quick forum post with no email announcement or anything if when we change any deadlines. Cool. And to be clear, we're not going to change any deadlines to make them less forgiving. We'll only ever extend the deadlines outwards, so to give more time. Okay, very cool. So that's a bit of administrivia. Does anyone have any like course questions? You still have workshops this week, as a reminder. The workshop tomorrow and Friday, they're shaping up to look quite interesting and get you playing around with traits. And we're going to be talking all about traits today. It's going to be very fun. So if you have any other like random administrivia things or confusions or anything like that, just feel free to post them in the chat. Otherwise, I need to turn off my notifications. Otherwise, we'll press on with where we left off. How do you doc test a function that returns a unit? So a function that returns a unit. Well, here's a good example, main, right? So I didn't write this here, main returns unit, but this is technically, it's kind of interesting. I don't think we ever mentioned this in the course. If you don't specify a return type, it's implied to be unit, and all functions sort of implicitly return, like if you don't have an expression at the very end, say like a string expression here at the very end of like 42 or whatever, they implicitly return unit. And so main is an example of a function that doesn't have a that returns unit. And I mean, I think I'm not 100% sure. Like maybe you've had some specific troubles with doc testing functions that return a unit, but from my understanding, it's just sort of like the same way as usual. It's, you can't really like, you won't be able to really test necessarily for the most part. It'll be very tricky in particular to test a function that's, you'd assume that it's sort of doing something like impure if you're coming from like a Haskell-y functional programmery perspective, in that the function works by producing some sort of side effect. Maybe that's a side effect that you can test for by like pulling in some other stuff potentially. But in the case where it's like, this is not really reasonable to make a small example to show off a test case, usually the doc test just comes down to like showing an example. So instead of like going assert that like calling main is equal to unit or something like, you know, something like this, usually you'll just go like, you know, I want to call main, so I do this, and like, you know, call main. And this will still get tested. It'll still execute the code and make sure it doesn't panic, and it'll it'll make sure that the function exists and you're calling it correctly and stuff. So it'll serve as an example, but it may not serve as a tested, like as a sort of traditional unit test with assertions and stuff like that. And if that's the case that you're in, then probably that's perfectly fine. Yeah, that's I think about, okay, yeah, cool. So if you're happy with that, then that's all good. If you want more, then anyone feel free to post on the course forum, and there might be some more interesting stuff to go into. But yeah. So, and Trey says, the doc test exercise is a bit strange with what specific functions need to be tested and made public. We'll be fixing that for next term. Cool. Okay. So we left off, to just quickly recap what we looked at last lecture. We were looking at generic type parameters. So yeah, we had a whole bunch of stuff here, blah, 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 blah. But in particular, this was the big thing that we managed to write during the lecture, which is this highly generic function that finds the smallest value in like the smallest value in anything that can be iterated over for any value that can be ordered, right? And so this could be like, you could throw a vec here, a linked list, a hash set, whatever. And you could throw anything in here. You could find like you could do an integer, floating point, a string, anything like that. And it will find you the smallest thing in that sequence, just with one sort of body of code here. Another important thing, and listen up to this one because it's going to be relevant to something that we learn about later on called trait objects, is that the way the compiler, like the way Rust sort of implements these generic type parameters is, so for example here, this function smallest 2 of t, it just like it looks through your whole code base, the whole sort of unit that's being compiled, and finds all the different cases that t may be. So it might find that, oh, we use like one case t is an I32, an F32, and a char. And then it goes, cool, I'm going to basically spit out handcrafted functions like this for each different type. So it essentially generates one individual version of the function for each type that it's used with. And this process, and like this eliminates all generic type parameters essentially. All the t partial order and stuff, that all gets checked before this this code generation step here happens. And then once all the like checking and everything is done, it goes, yep, all the types are good. It just spits out a whole bunch of functions, one for each type that it's used with, and almost like treats them as if they have different names and stuff like that. And this process we learned is called monomorphization, which is a massive mouthful, but it's a pretty important idea that we'll come back to later in terms of how the compiler does this. We talked about trade-offs with this as well, which is also quite interesting, in terms of the big ticket ones where, you know, you trade off things like binary size and compile time and all that, but you get very fast code that can be optimized very well. And it's also potentially a relatively simple optimization. And yes, as Trey mentions, it's also a zero cost abstraction in sort of both senses of the word, in that if you don't use generic type parameters, if you don't use this abstraction that Rust provides, then you won't sort of pay any cost for them. Generally, you won't pay the cost at compile time, like in the compile time takes longer, nor at runtime, in terms of, say, a bigger binary size of your code running slower. If you don't use it, then it's fine. You don't like pay the price for Rust having included this feature. And if you do use it, it's generally as fast as if you would have handwritten it all yourself anyway. Right, so those are the two sort of sense that it's a zero cost abstraction. Zero cost if you don't use it, and also, in theory, zero cost if you do use it. So this is a pretty interesting process, and it's a similar process that languages like C++ take, in terms of C++ has a similar idea called templates. Cool. So that's our recap of last lecture, and we left off starting to like look at traits and how traits vaguely work. I've also left my study window open over here, and sometimes the birds like to go a little bit sicko mode. If it gets annoying or distracting, or it starts leaking through, let me know in the chat, and I can close the window. Cool. So I think it'd be nice to do a quick tour of the standard library over some of these traits. We almost got to this point, and then we were like, but monomorphization, and then we finished off with that instead, which is an important idea. So we didn't really get to poke too closely at any of this, so let's have a poke at a few standard library traits. So what's an interesting one to start off with? Maybe something like ToString. ToString's pretty easy to start off with. So ToString here is a trait, and it's defined like this. So the trait definition is the sort of the big one we're interested in here. Pub trait ToString, and this trait defines one function, and it's a function called to_string. It takes a shared borrow on self, so a read-only borrow, and it produces a string. So as a reminder on how traits work, this trait can theoretically be implemented on any such type, like any struct or enum or whatever have you that you create. And when you implement this trait for some specific type, you need to provide an implementation of all the functions that the trait defines. In this case, and in a lot of cases, there's only one function that it defines, but you absolutely can write traits that define, multiple or many functions. In this case, it's just this one, and it must follow this same signature. So it must have the same name, the same parameters, the same return type, that sort of stuff. And in this case, it's a trait for converting a value into a string. So, for example, if I have the number 5, and I say let 5 is a string that is like the string 5 as opposed to the number 5, then that should be the same as calling i.toString. Now, there's an interesting thing that sort of comes up here. Why can we do i.toString in the first place? Well, I here, they haven't explicitly typed it, but I here will have type i32. And if we look down here at the implementers of this trait, so like what types implement the toString trait that the sort of standard library can see right here. And it should find that, okay, so it's funny that it's like, we don't see i32 here. It implements toString for string, for stir, for a char. Let's just look at this implementation for a second here. It implements toString for 8-bit numbers, i8 and u8. So potentially I'm betting, I was worried that this might be spat out by a macro or something, but it's not. Instead, we can really see, here's how they implemented toString for a 1-byte signed integer. And it basically like does what I think you would roughly expect if you were writing this code yourself. It creates a string with a default capacity of 4 to avoid sort of maybe need to allocate multiple times. If the number's negative, then it puts a minus character in front, and then it just sort of goes in like modulo 10. It goes, if it's bigger than 100, then push the 1, and then n divided by 10 plus, blah, blah, blah. It just sort of like constructs the number slowly and then goes, great, here's that string out the other end. And no worries, Miguel, just some like random announcements, and we're starting to look at traits. In particular, we're looking at the ToString trait. So yeah, I think this does roughly what we'd expect it to do. And if you were writing an implementation for i32, you wouldn't be able to do it exactly this kind of way. You'd probably need a loop and stuff, or a lot more code to deal with. If it's 10, 100, 1,000, 10,000, up to a couple billion. But there is this rather complicated impl here which does cover this i32 case. I'll try and read us through it, but it's a little complicated for now. It says impl on any type T, the trait ToString for that type T. So if this is where it ended off, like if there was nothing below this point, then this would implement the trait for literally any type T, which is, a little interesting, but it probably wouldn't be able to do much useful. But there's a constraint here. It says impl for any type T, the trait ToString for that T, only where T implements the trait display. Don't worry about the question mark sized for now. That's something a little special. But only where T implements the display trait, sorry. So if you implement the display trait, right? If you have my struct, right? Whatever you call it, struct my struct, and you implement display for my struct, then you'll automatically get an implementation of ToString for your type, which is kind of cool. To display is another thing that I put in this list here. And display here is sort of similar to the debug trait. It's another way of in effect turning a type into a string. Like it's very similar to a ToString, but instead of actually converting it to a string, it uses this thing called a formatter. And this idea of the formatter is it's almost like an abstraction over how you might like to see a type as a string, in that if you want a string, then you can format this into a string, and that's perfectly fine. But a lot of the time, if you have like, let's say it's a really big string that's going to get spat out, but all you intend to do is just like print it to the console, then you would rather just like read the type and write it to the console as you go, as opposed to allocating a huge string, writing all the bytes into the string, and then spitting out the string. You might as well just write it as you go and save all that extra work in constructing a string. So that's what the display trait basically does for us. You can see here that point will format as like this these braces, so like a parens 0, 0 in this case. You can see down here. And yeah, so in our case, we know that if you implement display, you get ToString for free. So if you're looking to implement ToString, a lot of people will instead opt to implement this display trait, and you get ToString for free, and you have the display implementation as well. So it's an interesting thing to keep in mind. So a couple interesting standard library traits to kick us off. And you see that this pub trait display again is just defining one function that you have to fill in. And usually you can just, again, follow these by examples and stuff like that to figure out, what's an easier, appropriate way to implement this trait. In our case, we see that this write bang here takes in F, which is the formatter that it gives you, and then it looks very much like the format bang or print line bang macros that we've already seen. So, it's still relatively convenient to use, I would say. And there's a whole bunch of implementations here, and you can see display is implemented for i32, and that's how the standard library got ToString. And I wonder, this is probably, this is implemented by a macro. We learn about macros in week 7, I believe. And yeah, it's a little gnarly, but you can see this is basically where the display trait is being implemented, but it's all this nasty macro code that's kind of hard to understand. We'll get like most of the way here to understand how this stuff works in week 7. Okay, cool. So a couple interesting traits there. Debug, we've already sort of seen a bit. Usually just derive it, get a default implementation of the trait, and in fact, actually, that's a nice thing to quickly look at. Let's go to a temporary directory, and I just want to show you something that I think is pretty cool really quickly. So if I do struct my struct here, and let's say it has X is an i32, Y is a char and z is a string, something like that. Something that you've probably found yourself doing from time to time is I want to derive clone on this. I want to be able to clone my structs, and the way that we told you, oh, you want to clone your my struct, the way we told you to do that is probably through this derive clone up here. But what does this derive clone code even do? I have showed this to a few students, like maybe four students or so at points during the workshops when they've come up and asked, how does this stuff work? But it's a lesson that's probably worth looking at in the lecture quickly as well. Let's just quickly look at the clone trait first, which is here. Trait stood clone clone. And you'll see, this is also interesting because it has two functions here, but one of them's a little fancy. Pub trait clone, so you can implement clone on some type. And to do that, you need to satisfy this function here, which says you define a function called clone, which takes a shared borrow of self. So again, you can only read it, you don't have ownership, and it should produce a new owned value of your same type. And in this way, you take a shared borrow of something that you don't own, and it spits out a new owned value. Now you have two potentially owned things. It's cloned it. It also defines a second function, clone from, but you'll notice that there's braces here, and then it's just sort of ripped out the body of this function here. This one here is a default implementation. So when you implement the clone trait, you must implement this clone function because it hasn't been defined, right? It's just a semicolon right here. And then you can optionally choose to implement this one if you would like. If you choose to implement it, then great. If you call this clone underscore from, then it'll use your implementation. If you choose not to implement it, then you'll get the default implementation, which they've written here, which will just do whatever this code is. So this is an interesting one. You could either implement one or two functions in order to implement clone. Is clone from kind of like stood move in C++? Performs a copy assignment from source. A.clone from borrow B is equivalent to A equals B.clone in functionality, but can be overridden to reuse the resources of A to avoid unnecessary allocations. So, like, sort of. Yeah, more like a copy constructor. Yeah, that sounds right. Again, I'm not necessarily a C++ expert, but that sounds about right to me. Someone who maybe knows C++ better than me might be able to shed some light as well. But that sounds about right. Cool. So you need to implement this function here, and if we didn't want to use this derive, we could still write this implementation ourselves. What would that look like? It'd probably look something like this: impl clone for my struct, function clone, and like you'll see, if I just leave it blank, I'll get an error saying, hey, you forgot to implement the function clone. I can tell Rust Analyzer to, oh wow, that's nice. Rust Analyzer can do all the work for me. I was just expecting it to do this for me. So it says create the clone function here, takes a borrow of self and returns a new self back. And reminder that this self here, capital self, is just an alias essentially for my struct. And we'd probably do something like, well, give a new my struct that goes, the x in my struct is going to be self.x, the y in my struct is going to be self.y, and the z in my struct is going to be self.z. However, we'll see that this line here doesn't work because writing self.z like this will try and move out of this string here. Like, these two types here are copy, string is not, and we don't have owned access, so we can't just move out of z. So we end up needing to clone here, and then this implementation will work. Now, something interesting is that if you were like a computer writing a clone implementation for a type, for just like any random type or any random struct, let's say in this case, you could like what's a pattern that you could follow here? Well, you could say just return back the struct itself with each of the fields, right? All of the fields here. And for each of the fields, I'm just going to say clone the field. Now, will that work for copy types like i32 and char? Well, yeah. Clone will end up just doing a copy anyway. Like, you don't necessarily need to write the .clone there, but it makes it simpler for like a computer. If a computer was doing it, just say .clone, 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 right? And so we could write this implementation ourselves, sure. However, we know that we can save a lot of time and energy, especially with a lot of these very common traits in writing hash derive clone. And let's see what I can tell Cargo to expand out all the macro expansions. Show me all the code that gets generated and stuff like that. And before I do that, I'm going to get rid of this print line macro because that spits out a whole bunch of random code. If you want to do this at home, you can simply do cargo, well, 6991 cargo install cargo dash expand, like that. And then 6991 cargo expand. And you'll see here, what does it spit out? Well, there's no longer this hash derive on top of my struct. Instead, we get this automatically derived impl clone for my struct. And it says function clone, my struct, x is clone self.x, y is clone self.y, z is clone self.z. So these hash derives are actually just spitting out these impl trait for type blocks that just sort of do it like mechanically, which is pretty cool. So that's a lot of these hash derives here are just implementing traits for our type, which is pretty cool. And if you want to look at those implementations, cargo expand or like cargo install cargo dash expand and then using it. It's a very fun and interesting tool to play around with. Any other interesting traits to look at? Partial eq and partial ord, I think we've looked at a reasonable amount. Traits like add, right? So this is a trait that gets invoked when you use plus, right? When you use the plus operator, it ends up calling the .add function from the add trait. And it almost feels like writing clone 3 times is a meta joke. If we look at their example here, you might have a struct point, right? This might feel relevant to some large task that we're expecting you to work on currently. You might have some struct point and you go, I want to be able to add points together with the plus operator. Great, no worries. Just impl add for your point. There is a optional generic type parameter here, right-hand side. It defaults, so this is like if you want to be able to add together 2 things of different types, like say the left-hand side is a point and you want to add together, say a point with just a single i32 and it maybe adds it to both x and y, then you could say the right-hand side is, you can, impl add where the right-hand side is just an i32 for a point, if you wanted to. And then if you add things together, if you add 2 of these things together, what type gets outputted? And they're saying, in this case, if you add 2 points together, right, because the default is for right-hand side is just self, which just means a point plus a point. Then what do we output? Another point. Self just meaning point, as a reminder. And how do they do this? They say, well, they have to define this function add here, which says you take in one of yourself and you take in a right-hand side of type right-hand side, which is also self in this case, and spit out an output, which again is also self. So take in yourself, which is a point, another point, and spit out another point. And you spit out a point, which is just your points x plus their points x, and the y is your points y plus their points y. And now, magically, you can add points together. Good point. Yes. And so this is quite handy. This is really cool. Oh, that's awesome. Look at this one. Let's see if we can try and quickly understand this. Imagine, so this was a point of i32s. But remember how in last lecture we were like, we can make this more generic, right? Like, why did we write an i32 here when we maybe didn't even need to do that? Like the only reason we chose i32s here is, well, A, because we wanted them, but why does i32 work? Because i32s can be added together, right? We're sort of like delegating point addition down to integer addition down here, but it doesn't necessarily need to be integer division. This could be really anything that could be added together. So they make it more generic. Make it more generic, right? So they go point of t, where it just contains an x, which is some t, and a y, which is some t, right? Where they are, given they're both t, then that also guarantees that x and y are of the same type, whatever that type is. And then this implementation here says impl, ignore this stuff for a second, impl add for point of t, impl addition over points of t, but only where the t, right? Only where t can be added together, right? With, again, they're sort of eliding off the right-hand side here, because it defaults to a t in this case. But it's basically saying where t's can be added with another t, that's the elided thing here, and they end up outputting a t as the output after addition. And the body just remains the same. We're making it sort of more generic here, and it all just works. But now if you had a point of, I don't know, like chars, or if you had a point of floats, or if you had a point of points of integers, whatever it is, they can all just be added together. Make it more generic, right? So this is a really cool example, which is very interesting, I think. And note that you can also, if this block here looks a little intimidating, you can of course do the where syntax. So instead of writing impl t add output t here, you can say impl t add for point t, and then use the where syntax down here like it was a function, where t can be added together to create an output of t. It's going, I don't know what add is. Yeah, I can help you with that. Use add. And it's going to be like, I don't know what point is. And I'll go, fine, I'll grab that here. And now it should be happy, probably. Yeah, it's happy enough. And what I was saying here is there's sort of like a right-hand side is t here as well, which it's... okay, whatever, that's fine. Anyway, regardless... So this is a very nice generic implementation for us to poke about at, which is yeah, pretty cool. Okay. So, any other particularly interesting things to poke at? Default we looked at in the other lecture as well, defining some sort of nice default for a type. Which is occasionally useful. All these different conversion traits, from, into, try from, try into, those are nice ones to look at. There's also some more complex traits here that are like, as ref, borrow, to owned. They can be a little confusing and look like they're like the same thing a lot of the time. And they're more about like nuanced borrowing and ownership rules, and help make code easier to write, but we're not really expecting you to touch these ones so much. FromStr is a cool trait. Lets you sort of define how you may construct one of your type from a string. And if you ever use .parse, that's how that worked, right? If you have the string 42 .parse into like an integer, that's working through the FromStr trait, which is pretty cool. So you define, there would be an implementation that's like impl FromStr for i32, and it has some code that basically converts a string into an i32, and that's how .parse works as well, which is pretty cool. And the error trait as well. I love, this is a great slide. Error traits, error. Error is a important trait. Where are we? Traits, error. There we go. Stood error. And these are all default implementations, which is also quite interesting. So you can implement error as long as your type implements debug and display, then you can implement error for your type. This is sort of like this overarching thing. If you have a type that's you're sort of using to denote some kind of error, it's a good idea to probably implement error for that type, especially since you don't even need to do anything like in order to do it. You could just do empty braces and leave all the defaults as they are. Super error is their example, I suppose. And you can see here that they have like they only implement one of these functions here, the source function, where it's basically saying, hey, this is the error, like that's the actual like problem, which is kind of interesting. But yeah, the error trait to sort of generally talk about errors, and then iteration traits as well. Iterator, IntoIterator, and FromIterator. So the really important trait here is Iterator. And iterator defines two important things. Why is next not showing up in the docs here? That's weird. I guess because there's so many functions, it just like collapsed them all. But iterator has two required things. You can implement iterator for some type, but you need to define what is the type of the thing that the iterator spits out, right? So if you have like a vec of strings and you say vec.IntoIter, then it'll give you back an iterator that produces, you know, item here is equal to string, and you define a function that says give me the next item, and if there's no item, just give me back none. Like if you reach the end of iteration. So this is a really important core trait in Rust, and you can see there's all these different functions, all sort of defaultly implemented on iterators that help you do things like, you know, dot filter, dot map, dot skip, dot take, dot collect, dot whatever. I'm just reading out random functions at this point. And then a couple traits that sort of define that your type can be turned, can produce an iterator, let's say. So for example, we have the IntoIterator trait here, and a vec will implement IntoIterator because it can be iterated. Like you can, if you have a vec, you can create an iterator out of that vec that you can then iterate over. And this actually exists in like most modern languages, you know, your Javas of the world. I think Java calls this iterable, and like it has a distinction of iterable and iterator. I'm guessing the cool thing is that with all the ones other than next are automatically implemented, but you can find them yourself to potentially make it more efficient. Yes, absolutely. Very, very wisely noted. And so, but yeah, IntoIterator, something that's quite interesting about IntoIterator as well is that often people will implement IntoIterator like 3 times. So notice here, in the case of vec, it's implemented for a shared borrow of vec, a exclusive borrow of a vec, and also for a vec itself. And what's the difference between all these implementations? Well, if you own the vec itself, then the iterator that it creates will spit out owned t's. If you have an exclusive borrow on a vec, the thing it spits out will be exclusive borrows of t's. And if you only have a shared borrow of a vec, the items it spits out will be shared borrows of t's. And the actual iterator structs that it produces are different things here: iter, IterMut, and IntoIter over here, which are slice iterators, and then a vec iterator over here. We'll look at writing our own iterator across a vec at the end of the lecture, which is pretty cool. You can only do hash derive if all functions in a trait is implemented right. Not quite. I think that's quite the way I'd put it, because so in the case of error, oh, there it was. I couldn't see it before. Error, you can just sort of do like impl error for my type here, and then just do empty braces, like open brace, close brace. Oh, sorry, right. Yeah, I think Shrey might be finding the misunderstanding here in the all fields in a struct. So this is an important idea where I did like hash derive clone on my struct, but that's not going to work if I have a field in here that doesn't implement clone, because clone needs to go through and clone. The way it spits out the implementation is by cloning all the inside fields. So I might have a struct foo here that doesn't implement clone, and then the implementation of clone will not work because it goes, hey, I don't know how to clone a foo. Even though maybe you full well could impl clone yourself, and you might have to do that. Function clone, self, x is self.x, y is self.y, z is self.z.clone. And then you could write something like foo is just create a new foo. And so there are cases where maybe you might be able to implement clone yourself, but the derive macro is not smart enough to figure it out for you. That might be sort of the way you're going down there. Cool. Anyway, so there's also FromIterator. If you've used .collect, that's basically, you know, you're in iterator land, you've done a bunch of stuff, and now you want to put it back into a collection. FromIterator ends up allowing that .collect method to be called at the end of your big iteration chain. So in fact, if we go back to Iterator for a second and we go to collect the function, collect, you'll find that collect will collect into some collection they call B, I suppose. Any collection B is happy to collect into as long as B implements FromIterator for this kind of item. So there would be an implementation of FromIterator for, say, a Vec, for, say, a Vec, for a Vec, where a Vec can, you can create a Vec T from any FromIterator of T. There's no requirements on T here. But, say, a hash set, if you wanted to collect your items into a hash set, there is a requirement that you can hash and check for equality the T's that you're putting in there. Because that's sort of like a requirement for a hash set to work, is that you need to be able to hash the T's that you put in and compare them for equality if there's some sort of hash collision. So that's also quite interesting. A Vec, supports any T's. A hash set you can collect into only if the T supports, equality and hashing. And similar things for like, binary tree sets and stuff where it's needs to implement ORD, like strict ordering and that sort of stuff. Yeah, or you can collect a whole bunch of chars into a string, all kinds of fun stuff, naturally. Cool. So I think that's our sort of standard library tour of a whole bunch of common traits that you're likely to run into. Focus your bloody camera. No? Okay, there we go. I don't know what's wrong with the thing sometimes. Probably the lighting, actually. Yeah, we'll do that. All right. So now we get to play some with some traits ourselves in this traits example that we've got here. So traits. Oh, look, the animals have come out. We've got a sheep and a cow. Two different structs here. And again, naturally, if you have any questions. Oh, I missed also Kai saying, so if you can do derive, it's the same thing as doing impl for empty braces. Yeah, not quite. It's more like the standard library has defined a macro, like some code that can take in, say, a struct or an enum or whatever, and spit out a impl trait for that type. That they sort of write the code for that implementation as code automatically for you, as opposed to traits that have no required fields. They're not necessarily derivable. The derive macro would be very easy for it. It'd just be impl trait for type empty braces, but also you could just write that line of code yourself. I don't think like in particular error is a trait that has no required functions, but I don't think there's a derive macro for error because you're expected to just do impl error for type empty braces. Macros. But the bloody derive macros don't show up in here. Is there any way I guess I can just do it by testing hash derive error. I don't think, there's no error derive macro, for example. Anyway, so onto our traits example here. I have a sheep and I have a cow. No crab. Yeah, actually, that's a good point. Well, I apologize, but sheep and cow is what we've got. And you'll notice that they have different properties. So they both have a name and they both have an age. Every sheep and every cow has a name and an age. But they each have their own sort of like differentiating fields that I've put in here. A sheep in particular, it's important to know whether the sheep is currently attending a party or not, right? True or false? False, they're not at a party. True, they're currently at a party. And a cow, it's important to know whether the cow's angry or not, right? Angry cow or non-angry cow. Maybe we can consider that to be happy cow, but I suppose neutral cow might also fall into that category. So I've got some different animals and they've got different properties, but I'd like to be able to sort of talk about the idea of an animal more generally, right? Like, this is, what I've written here is all well and good, but there's no real relation between sheep and cows that I might actually I might want to sort of take advantage of, to be able to use them sort of in the same, almost in like the same idea in my code, right? So I might want to write a trait to unify these kinds of types. So in this case, I've written a trait animal, and the trait defines a few functions that must be implemented. It defines a name, right? If you ask for the name of the animal, you've got to spit out a string. If you ask for the age of an animal, then it gives you 32. You also must define a function speak, which should spit out a string, which is, you know, how the animal speaks. It says something. And then a slightly more complicated function here called say hello to, which you have to implement on your particular animal, such that if it takes in another animal, right here A, where A is some animal, then it spits out a greeting from like one animal to another, right? So like if I implement animal for sheep, then I need to be able to define these three things here, and also how a sheep would say hello to any other animal, A in this case. And it might want to sort of use the information about this animal here in order to figure out how it would say hello to it or not. So I've got some animals up the top here in main. So let Sean equals a sheep, which has the name Sean. Its age is 4, and it is, in fact, currently at a party. And we have Betsy, which is a cow with the name Betsy. It's 10 years old, and Betsy is currently not angry. Right, and then I tell main to make Sean speak, make Betsy speak, and then you can see here how that say hello to function is working. Sean say hello to Betsy, Betsy say hello to Sean. Okay, so how might I implement the animal trait on these animals? Well, I've got a couple of implementations down here, and let's take them slowly, I suppose. So you see here I've written impl animal for sheep. So the first function it requires is the name, which produces a string. And you'll notice I've just done self.name.clone here. Note that we only have borrowed access to self, so I wouldn't just be able to say self.name, because I can't move out of self.name, which is behind the shared borrow. So instead, I'll just clone it here. This function could very much probably just return a ref stir. Like I could define this trait to, instead of spitting out a string, spit out a ref stir, which is, you know, borrowed against self. But in the name of simplicity and not have to think about like live types or borrows or anything like that, whatever, we'll just clone it. It'll work. Next up, we have give the age. That's a copy type, so that's very easy, just self.age. And then we have the function speak. And you'll notice that a sheep can have specific behavior based on whether it's at a party or not, right? Because we're implementing this for a sheep, so we know the properties of that sheep. In particular, we can say if it's at a party, the sheep can say butts, 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 and has an emoji, which it somehow communicates verbally, I suppose. Whereas if it's not at the party, I'm assuming it's just going to go bah, right? A top-tiered sheep impression, naturally. And so we can have sort of behavior that's predicated upon the fact that this is a sheep. And then to say hello to another animal, right? To say hello to any animal A, right? We have a shared borrow in ourselves and a shared borrow of that other animal, where A is some animal. And we say, if we're at a party, the sheep will say, how's the party? Yes. And it also puts in the other animal's name here. So it asks the other animal how the party is. Once again, conveying these emojis verbally, I suppose. Whereas if it's not at the party, it just says bar to you with the animal's name. Right? Did Tom write these puns? No. This was part me and part my partner. Coming up with these horrible things here. So naturally, we also have an implementation of animal for cow down here. So you have self-name, clone, self-age. So notice that these are, you know, pretty similar because they have pretty similar properties. I guess this is less fun, maybe, the cow one. If the cow is angry, it just goes moo. Whereas if it's not angry at the time, it's moo. You know, it's like a normal cow moo as opposed to angry cow moo. And then to say hello to another animal, If it's angry, it goes moo you, other animal. But if it's not angry, it says moo with the other animal. And it also verbally manages to communicate this one here. So there's all our implementations, right? A cow is now an animal, according to this. And a sheep is now an animal, according to this. And so now we're ready for some action, right? So since they're an animal, we can call these trait methods on these sort of concrete objects here, like this concrete sheep, this concrete cow. I can now say speak, say hello to, even though the struct itself doesn't implement these functions. The traits that it implements does, and so I can call those functions. Note, something interesting is that it is important that in order to call the methods, these methods sort of have been defined by these trait implementations down here, which are implementing this trait animal. In order to be able to call these methods on the type, the trait itself also needs to be in scope. So what do I mean by that? I mean that if this trait animal was defined in a separate module, a separate file, an entirely separate crate, anything like that. So let's say I'm going to call it mod animal trait here. And let's say we have the trait in here, and let's say we have the trait and the trait implementations. The trait implementations don't need to be in here, to be clear. But I'm doing it to make the scoping a little easier for myself in this example. You'll notice that if if all of these are in a separate module here, it no longer knows what these functions are because it doesn't like see the functions having been defined by this trait animal, which also I'm going to need to sort of make public to the crate, I suppose. It also doesn't know what sheep is, so I need to tell it to use a cow and a sheep, which is funny as well. And so the easy fix for this is just bring that trait into scope. Use animal trait animal. And as soon as it knows that trait exists, like you've just brought that trait into scope, then it has no problems calling these methods. Note that this use could be really anywhere that's visible from wherever the code path is. So I could put it, it's pretty usual to put it up here, something like that. And again, these functions become available to you. The compiler is usually pretty good at guiding you through this kind of stuff if you get lost or confused. It'll say, hey, I can't find this function, but I did actually find it. I just, you need to do this for me in order for me to do that for you and all that. And so we can speak, say hello to. So let's double check this actually works. Cargo run. So the Sean says hello and Betsy says hello. And then Sean says, how's the party, Betsy? And Betsy says, moo Sean. Which is naturally just fantastic. Yeah, so we've got our first little bit of using traits here. Now, we're going to do a whole bunch more with these traits over the next, half hour or so, but I think it's a good time to take a quick break. It's 3 minutes past. Let's come back at 7 past the hour. We'll play around with these traits. We'll play around with something called trait objects, and then we'll do these cool sort of using the Iterator trait as well in a little bit. We'll come back at 7 past, and we'll continue on. Cool. See you all soon. All right, and welcome back. Here we go. So let me see what the chat's just saying. How does a trait definition usually handle not knowing about the other objects, i.e. how to avoid use super cow sheep? So this is just because we've named sheep here and named cow here, it doesn't know, like, impl animal for sheep. What's a sheep? So I just had to use this use thing here because it's in a separate module. Often you'll define, like, notice the structs were defined outside the module over here. Usually it's pretty common to define your trait implementations and your struct right next to each other. So you don't need to do this, like, use, you know, to import, I suppose, the things, the structs you're implementing on and stuff like that for the most part. But sometimes you might want to define your own trait like animal and say, you know, something strange like impl animal for some completely foreign type, like Vec. I don't know, like apparently a Vec of whatever is a valid implementation of an animal. And you might need to pull in that foreign type with an import statement if it's not sort of like a default import of the language. But it's not something you usually run into, and it's just because you're naming the type over here, and so it just needs to know what that type is. I suppose since I made the point about the trait definition needing to be in scope, we can get rid of all that code as well now, and things are just fine again with no users or anything like that. I noticed some repetition with the implementations of age, but then it seems we can't give a default implementation of the trait because the trait doesn't know about its implementers fields. Yes, so absolutely correct. Any way around that, or is it just a trade-off we have to accept? It's an easy way around that is not necessarily coming to me immediately. Usually it's yeah, nothing super obvious immediately, to be honest. Yeah, it's an interesting point that you bring up, regardless of there maybe not being an obvious easy way around it necessarily. Yeah. Okay, so to keep moving, we've used these concrete types over here, and then we've called methods on them. And since we've defined our own trait here, we can also use this trait in generic type parameters, right? So we could say, for example, define a struct BestFriends, struct BestFriends, that takes in two different types of animal 1 and animal 2, and animal 1, I suppose, and animal 2, keeps them as fields like this, and then simply define functions for any animal 1 and animal 2 on BestFriends of animal 1, animal 2. Define functions to do common things. Like, for example, we do like function both greet, right? A borrow of self. They both greet, or a function say hello to each other, right? That also produces a string, and we could write code that does something like this. Now, something's going to go wrong, which is going to be fun. If you've spotted it already, then I'm very proud of you. So we might do something like we're going to need to sort of join the greetings together, I suppose. I guess we can do something like a format this new line that, and self.animal1.speak, as we've seen down here, self_animal1speak, and self_animal2.speak. And this is going to lead us to an error. And I'm not going to show the error message. Why are we getting an error in our function definition here? Anyone want to take a stab? Why is this here causing an error where it's causing that error? And I'm being very mean and not even showing you the error message. Lifetimes? Maybe. Might be a little too deep in the source if we're thinking about lifetimes. Right. A1 and A2 are just any types. Right? A1, A2, A1, A2, A1, A2. Never did we specify any kind of restriction on what A1 or A2 could be. So like speak is no method named speak found for type parameter A1. And the compiler is so smart. The following trait defines an item speak. Perhaps you need to restrict the type parameter A1 with it, :animal. Huh. Like, Rust is tricky. Rust is a difficult language, but the compiler, like, what other compiler is smart enough to tell you, like, oh, I think I get what you mean here, and like you might want to say that like these are animals here. Like that's something that I really like about the something that really cool about the Rust compiler. And so we'll specify those restrictions. So where A1 is an animal and A2 is an animal as well. And now this function is perfectly happy. So fortunately no lifetimes having been run into. Focus camera. Okay. Cool. So that's pretty awesome. Now we could also, there's two different places we could have specified these type restrictions here, these type bounds. I guess if I'm going to do it there, I'm going to have to do it here as well. I could have specified them on the struct or just on this implementation. And there's genuinely a fair argument in both cases here for what might be the best. The Rust community in general opts to not specify the restrictions on the struct, but only specify the restrictions sort of where they're required. There's a few arguments to this, a few different perspectives, and some of a portion of the perspective is just like is like it makes writing code easier, because if you do it up here, then there's annoying things you have to think about that you don't necessarily have to if you just do it down here. But it's a pretty long-winded discussion. So if anyone's interested in sort of putting it here versus putting it on the struct definition, ask a question on the forum, and I'm happy to write up a big post all about it and link to some interesting stuff. But I'm going to just sort of specify the restriction down here, and we should see, like, you can create a BestFriends struct with any two types. You could say A1 is an I32 and you could say A2 is a string, right? But you're not going to be able to call both greet and say hello to each other unless both those types are animals. So that's sort of the restrictions we're placing on this. And then naturally we can write this code down here as well, where it says hello to animal self.animal2. And this will say hello to self.animal1, like that. And ta-da! So now we could simply say, let BestFriends equals BestFriends, where animal1 is Sean the sheep, like this, and animal2 is Betsy the cow, like that. And then simply println of BestFriends dot say, what do they call it? BestFriends dot both greet, BestFriends dot both greet, and BestFriends dot say hello to each other. And in theory, this does the same thing, right? So now we've managed to write some code which is generic over this animal trait that we created, that maybe does some interesting stuff. So that's great. We've got some BestFriends happening here. So that's pretty handy. However, we're about to run into a pane of rust. Which is, and this is a very natural thing to want. What if I want a Vec of Animals? Right? Now, how would you sort of like type that out? Well, there are some different ways you could say it. You might go, oh, okay, I know how to do this. Let's say I want a function that's like all animals greet, like this. And we're going to take a animals is a Vec of, well, let's say a Vec of A, where A is some type that we're specifying here. Say this goes to a string, where A here is animal. Why did I put the braces there? Great. And we say for animal in animals, animal dot speak. Or okay, fine. Let's just make this not return a string, and we'll just print line it instead, just to make our example here a little easier. Animal speak, like that. And I suppose this doesn't necessarily need to be a Vec. It could be a borrow of a Vec, and that could then be a slice, as we've learned and all this. But whatever. I'm just going to leave it as a vec for now. All animals greet. Now, does this work? Is it going to do what we want? Well, let's try it out. Let me say, I guess we'll just do it above here. Let my vec equals vec bang of, let's just do a couple sheep. Let's do 3 sheep. Sean, Miguel, and Alex. I hope you're okay with being sheep for, I didn't mean that, but like, I hope you don't mind sort of being part of the barnyard here, I suppose, for our examples. And we're going to say, call the all animals greet function with my Vec of Animals. Now, does this work? Yes, it does. That seems to work. They're all sort of happy, enjoying themselves at the party. But let's say Sean is no longer a sheep. I don't know if either of you really want to be a cow. So I guess we'll change Sean. Sean is no longer a sheep. Sean is going to be a cow. And Sean fortunately is not angry at this time. Now we run into a problem. Oh no, we've got error messages. This was meant to just work, you know, it was all meant to be great. And notice that this vec here can really just be thrown inline here as well, without the semicolon naturally. And it's no good. Is there any reason why you even need to give the format string even if you're printing a single thing for println? This is sort of Rust's defense against format string vulnerabilities. Fortunately, it does all the formatting at compile time. You could reasonably suggest that if the println macro sees something that's not a string as the first thing, it just prints that thing as a string. But they chose to not do that to make it very clear that this is formatting and that it's not something that might be vulnerable to format string injection, which is a whole sort of thing in C that's a little out of scope for right now, but perfectly welcome on the forum naturally. So this doesn't work. Can anyone suggest why this might not work? Vec of animal, right. So this is like, this is not quite an answer to the question. Like, sorry, like the way I've structured this is a little misleading, but I think writing it this way is going to potentially help explain why this doesn't work. Even though if you're an advanced Rust person, you might go, he's not explaining the actual error, he's explaining it a step further along. But anyway, I think this will work best. But yeah, Vec doesn't like different types. Vec needs same type, blah blah blah. Great. So the idea here is that this A is sort of is a generic type parameter that represents some type, and we know that type must implement animal. And we take a vec of that A. But at the end of the day, A will be instantiated to be some actual concrete type. And so once it's instantiated to that, let's say cow is first thing here, then really what we're asking for is a vec of cows. And remember, it's going to generate one function for each type it's called with. It's not just magically going to handle having vecs of all different kind of A's, right? We'd almost need like A1, A2, A3, A4, and so on. Like, if you knew how many animals you had in advance, you could make something like this work, potentially with something like a tuple or a whole bunch of arguments. But if you want some arbitrary amount of animals, this simply isn't going to work, because A is just generally going to be one type. And vec needs to know size. It's can't have a vec of traits. So this is, note that this is not yet a vec of traits, and that's the important thing here. What we kind of want is a vec of traits, but instead we have a vec of this type A, which is going to be like whatever, like the Rust compiler will figure that out when the function is called, and that A is just one type. So we really want a vec of animal, but a vec of animal is not going to quite work straight away either. Vec of animal, like this, right? Save the file. Does it work? No, almost, you know. Oh, there's only one tiny little error. Maybe it's not so bad. It says trait objects must include the dyn keyword, din. Add din keyword before the trait. You can call it din, you can call it dyn. I don't care. It's fine. That was Dr. Seuss right there. But it stands for dynamic, which is, you know, where the dyn comes from here. But it goes, okay, just throw din before it. Okay. Din animal. Okay, the error got bigger. It's got the size for values of type din animal, also plus tick static here. That's a whole nother thing that we're not going to worry about for now. Cannot be known at compilation time, blah, blah, blah. So what's this complaining about? The thing that it's complaining about now is that you have a vec of these animal trait objects here, right? And this is where we get into this object terminology here, trait object. And conceptually, this is a vec of any kind of struct where that struct implements the animal trait. So in our case, we only have where are they? Where'd they go? We only have sheep and cows, right? But presumably we could also have other things here. Like we could have struct crab, as someone mentioned earlier. And maybe a crab doesn't have a name, right? All crabs are implied to have the name Ferris. And a crab just has an AG32. And so you might go implement animal for crab. And their name is always just string from Ferris. And their age is self.age. And they speak, all they say is, I don't know, crab noises. And to say hello to, they just go format. They say something like attacks blah with clause animal dot name, something like that. So it attacks the other animal with its crab claws, right? The interesting thing that's happened now is not all animals have the same size or the same layout or anything like that, but importantly, not the same size. This here has a string, a U32, a bool. This has a string, a U32, a bool, even though they're like different types. These will end up probably having the same size, but a crab is a completely different size. And vecs, right? Most things in Rust, most things in Rust really care about their size, right? In the case of a vec, the way it works is it has a pointer into this sort of allocation here where we have, you know, let's say it's just numbers 1, 2, 3, 4, 5, 6, 7, right? Where each of these numbers is a fixed size. So let's say they're each like 4 bytes or something like that. And if I say vec, I want like the third element, well, it's going to go, well, here's where it starts off, right here. And I need to go 3 times 4 bytes across, right? I suppose that's probably here. And it'll get you to the element that you're looking for. But if we now have like cow, sheep, crab, cow, crab, like suddenly this starts breaking a whole lot of the stuff that's sort of important in Rust, in that these can all have potentially different sizes, whereas Rust very often really cares what the size of a certain type is. Right. And so then Simon comes across with an idea. How about instead of doing din animal here, because this is not sized and Vec is saying, hey, the thing that you want me to be a Vec of, why is it not giving me the error? Here we go. The thing that you want me to hold in the Vec, I need to know what the size is. And basically anytime you write, you know, there's an implicit thing here, which we sort of ignored a little earlier. Whenever I introduce a new type parameter here, A1, A2, something like that, the compiler always says, it explicitly says that A1 and A2 must be sized. Implicitly rather, inserts code that looks like this for you. That requires that basically anytime you're dealing with any kind of random type parameter, it goes, I'm going to assume you want to know the size of that thing. Because if you don't know the size of the thing, it's really hard to do anything with it in Rust, which is the exact problem we're running into here. So Simon mentions, well, a box ends up just being like a pointer. It's just a pointer into the thing that you want. You'll be able to still use that thing you want, but a box has a known fixed size. A box is always going to be, just give me 2 seconds here. Okay, I think it's fine. Can you hear and see me and stuff now? Stream is healthy. That's so weird. I got a call and it goes, let me just switch that internet off. Good now. Yeah, okay. That's a fun moment. I apologize for that. I will pray that no one else calls me, because I don't think I can just turn off calls without also turning off my data. So that's really, I'm glad I know that now. Anyway, so the idea was a box is a fixed size, right? Yeah, don't DOS the lectures, please. A box is always a fixed size. It's just going to be one pointer. And so maybe a Vec is happy to hold a box of something that it doesn't know the size of. The other thing that's important here is if you look at box, the definition of a box says that a box can hold some t here, right? The type that the box contains. And it explicitly says that that t doesn't necessarily need to be sized. It can have like an unknown size, and I'll keep track of that size, you know, so that's no worries there. So that seems good. And the error's gotten smaller again. And now we get to this really sort of painful bit here. The trait animal cannot be made into an object. And this is one of the most, the biggest thing the biggest problem you'll face with traits in general. So here's a nice like tip. Simon was absolutely right. I think it was Simon that said, I got to scroll up in the chat now because of all the Fs. Yes, Simon was absolutely right in that when you're using like din trait, you almost always want it behind something like a box or a borrow or something like that. Note that a borrow also has the same behavior like a box, where it'll, you know, it'll do what you want. It'll take something that it can point to something that has an unknown size, and give it like a fixed size by being a pointer. And basically the question is, do you want to own it or not? Do you want, like, if you want shared access, then use a shared borrow of a din animal. If you want exclusive access, an exclusive borrow of a din animal. If you want owned access, usually you just say use the t itself. That trick no longer really works for us because we don't know the size of it. So we just say throw it in a box, because a box sort of implies ownership. And so that's your sort of, if you want the cliff notes on using trait objects, then that's sort of the trick for it. Now, the problem here is that animal, the way we've defined this trait, animal cannot be turned into a trait object. And I can explain why, but it's a little tricky. So focus in for a couple minutes here. I'll explain why animal can't be made into a trait object. I'll show you where you can find the rules for trait objects in Rust. I'll apologize profusely for like you having to think about all these rules, because it is a pretty annoying part of Rust. And then we'll fix it and make it work. So the problem with the trait animal is this function right here, say hello to. The reason there's a bunch of things that can stop a trait from being turned into a trait object. This function is currently doing it for us. And the reason why is it has this generic type parameter on it called a. Now, the reason this is a problem is that we know that when we have a generic type parameter, the compiler will look for all the different places where it was, where say hello to was called, and it'll generate a single function for each type of animal that it was called on. And then when it finds the types that it's been called with, yeah, it generates that function, and then where it was called from, it just calls that function directly now, right? So where does that pose a problem for us with trait objects? Well, with trait objects, you have no idea what animal this is anymore. You have no idea what animal this is anymore at all. And so the question is, it's this tricky to get my wording quite precise here. If you don't know what animal, whatever like this din animal here is, and you want to say hello to another animal, right? Which is also, let's say, another din animal in this case, you don't know what either of their types are, and therefore, like, which say hello to function do you call? Because there'll be like a few different versions of say hello to cow, say hello to sheep, say hello to crab, that kind of thing. But if you have two animals, right, and you don't know the type of either of them, you don't know which say hello to function to call. And so one of the rules, basically, this is a blanket rule, which they're working on reducing the restrictions on trait objects, but it's something that's going to certainly take a long time, is is so in our case, if you have a generic type parameter on a function in a trait, can't be a trait object. Now you have two options from this point forward. Sorry, you have a few options really. Here's a couple that I can point out. Let's say you want to make this function work for the trait object. You really care about saying hello to with an animal that you don't know the type of. The solution there is exactly what Dong said. Make the function use trait objects as well, as opposed to using these generic type parameters. Right? They mostly achieve similar ideas, generic type parameters and trait objects. But generic type parameters act monomorphically, as we know, where it creates these functions at compile time, whereas trait objects don't know the type until runtime. Like as the program's running, it works more like a language like Java or C++ or whatever. So we can change this. So instead of using a generic type parameter like this, it simply takes in a refdin animal like this, right? Our trait implementations are now going to probably be wrong because they're still used to this old format here. Refdin animal, din animal, like that. Get rid of the A here. And this one here for the crab as well. Din animal. Like that. And then up here, the only error that we've got at this point, like you see this function's now happy. All it's saying is that, hey, you gave me a cow, but I needed a boxed in animal. Oh yeah, like I forgot the box, right? So you just throw box new around this cow. And then similarly, you throw box new around the sheep. And it all works, right? Let's see if the animals all greet. Moo, butts. Yeah, that seems right. And just to yeah, so this is now the animals are all greeting. So that's one option, is convert the function in the trait such that it doesn't have that restriction. Instead, it uses a trait object and everything's okay again. Cow in a box. Yes, cow in a box. Now, another option is you might go, well, like this say hello to function is all good and well. If I'll go back now to what we had before, which was here. I think that's where I want to leave off. And it's going to be saying, hey, yeah, this can't be a trait object anymore. Good. Maybe what you go is actually trait. Like I would like to use a din animal. I'd like an animal trait object, but like I'm happy to just not include this function in the trait objects. So if you have a din animal, you'll have access to these three functions here, but it'll just like forget that this function even exists on a trait object. You can still use this if it's not a din animal, if it's just like a cow or a sheep or some animal as a generic type parameter, but just don't include this function in the trait object and leave it otherwise. So there's two ways you can do this. One is you could move this function into a separate trait. So you could say, for example, trait animal say hello, and this requires that you're an animal in the first place potentially. That's sort of this, it's not quite inheritance, it's more like a restriction on the types that can implement this trait here. So to implement animal say hello, you got to first make sure you've implemented animal, and then just move this trait out to a separate thing, implement them all separately, and then you only do a boxed in animal in most places, and then you do like a animal say hello where you want to use this function outside of trait objects. That's also a potential solution, but can get a little confusing and a little annoying at times. And there is one very special escape hatch in the Rust compiler where this is the trick that I generally opt for if I just want to not include this function in the trait object, but still leave it there for normal trait parameters as opposed to like the objects, which is in this where clause, you can add in a self-sized, this sort of magic incantation here. And you'll see this is now working. Of course, we need this whole box business again. Box new, and box new, and the closing parens. And this also works just by adding this where self-sized. The reason this trick tends to work is trait objects, as we know, din animal, are not sized, right? They are, in fact, a trait object is never sized. So that's why we always have to put it inside a box or put it behind a borrow or something like that, right? Since it's never sized, Rust sees this constraint that I put here where self-size, and it goes, right, you're saying that this should only be included on things that, have a size, and it chooses to opt the trait object out of this function here. So you'll notice that now we can use trait objects. We can still use say hello to each other when we're not using trait objects, when we're just using the monomorphic generic type parameters. But when it's a trait object here, you'll notice if I look at the functions available, I have age, I have name, I have speak, but say hello to here won't work. Let's say it's not going to work to say hello to itself, but actually maybe it would. But it says here, say hello to method cannot be invoked on a trait object, right? Because it has a sized requirement. So this is a good thing to know about. It's good to know about this escape hatch in the compiler where self-sized, to just like include a function in a trait, but don't include it in a trait object because it might be preventing you from being able to create a trait object. So where is the list, like a comprehensive list of these rules? The answer is you look for Rust object safety. These are the object safety requirements, and it's an object safe method must meet one of the following conditions, and these are the important ones here. Is that you must not have any generic type parameters. You can't use like there's a couple of restrictions on things you can use like self here, and must not use self. If you run into them, the compiler will stop you and say, here's what's going on. If you just want to opt it out, then you can just throw that where self-sized magic sort of where clause on it. And if things are getting really complicated and you're confused, you can feel free to ask about trait objects and stuff like that on the course forum as well, and we'll help you walk through it. But that's our sort of introduction to using things as trait objects. And you'll see now that this Vec boxed in animal can hold all different kinds of animals in like one single collection as one single thing. And that can often be very helpful. You do pay a runtime cost for this. So note that compared to monomorphization, you don't have to generate a whole bunch of all animals greet functions. There will just be one, which is really handy by using a trait object. But it means it's going to be slower at compile time because you have to follow pointers. It has to use something called a V table. There's all kinds of interesting stuff in terms of the implementations if you're interested in it. But there's, those are the rough trade-offs that you're making there. Okay, trait objects. That is basically everything I wanted to talk about in terms of these traits here. Our last thing in the lecture is just going to be implementing the Iterator trait for a couple things, which will just be, I think, mostly quick and fun. But we'll pause a little bit for questions about any of this. We'll move on with that stuff. The stuff at the end, I think, should be relatively quick, and that'll be it for like Flexi Week and stuff. So slower at runtime or compile time, sorry. So trait objects are faster at compile time, slower at runtime. Generic type parameters are slower at compile time, faster when running the program. Is C++'s object slicing its own way of getting around this since they have inheritance? I am not entirely sure. I've meant at a few points in my life to have a big mess around with how C++ deals with all of these problems, where Rust at this point has mostly just like thrown its hands up, and I'm not well versed enough in the like low level details of how C++ implements like its V tables and its object rules to be able to answer your question confidently. But if you ask on the forum, you can certainly prompt me or maybe someone who also knows more about C++ to really get into those details and see how it deals with some of these. But one thing I will note naturally is that Rust is working on trying to reduce the requirements on object safety over time. It's just naturally a very difficult process to work on that. But it's a great question for sure, because C++ doesn't have these kinds of strict requirements as I understand it, but of course they make their own trade-offs along the way as well. And object slicing is, as Miguel's saying, object slicing is the issue we're avoiding. Interesting. Okay. Any other questions? Naturally, all this code is on GitHub. It's under like the Lec 09 because it's the same sort of series of lectures. I have linked the code on the website to go to this one as well. So, and I'll push all the changes we've made as well today after the lecture. So I'd suggest having a look at this code again and poking around in it and, you know, playing with things yourself and asking lots of questions on the course forum naturally, all of that. And you two are having an interesting C++ chat that is a little too above my head for me to get in on, sadly. But I'll happily leave you to that. So that was some trait stuff. Now we're just going to implement a couple traits, and I think it's going to be fun. So I'd like to implement the iterator trait specifically. So Iterator, as a reminder, is a trait that requires you to define two things: the type of the item that the iterator spits out, and then a function to get the next thing, you know, if it exists. That's why it returns an option here. And then it gives you all these sort of functions for free as default implementations on the trait. Now note that the iterator trait is for something that is to be actively iterated on. So that's distinct from the IntoIter trait. That's distinct from the IntoIter trait, which essentially takes a thing that could realistically be iterated over and actually creates an iterator for it. So note that if we have something like Vec of I32, then Vec gives you things like IntoIter, which is what the IntoIterator trait is, and convenience functions like iter and iter, oops, that should be an underscore, mute. And each of these functions here gives you back gives you back a struct. This one is called IntoIter. This struct here is called iter. And this struct here is called IterMut. They're just Vec's own structs as far as we're concerned. And each of these has an actual implementation. So there's an implementation here, IntoIterator for like, you know, each of these types here. IntoIterator for IntoIter, IntoIterator for iter, IntoIterator for IterMut. But notably, there is not IntoIterator for Vec. Instead, there's things like IntoIterator for Vec, and also IntoIterator on a borrow of a Vec or an exclusive borrow of a Vec and stuff like that, as we saw earlier. So it's the difference between something that could realistically be iterated over. Again, languages like Java might call this iterable, and the actual iterator itself, the thing that's like we're like 3 elements in and where, you know, the next one you can ask me and I'll give it to you and that sort of thing. So we've got 2 iterators I'd like to make. The first one is a Fibonacci iterator, which just produces elements of the Fibonacci sequence, and then a Vec iterator that lets you iterate over the elements in a Vec. I think both of these are interesting for their own reasons. And note that the Fibonacci iterator in particular will be infinite. There is no realistic end. Well, I suppose overflow is... maybe overflow is a nice end to the iteration, but iteration in Rust can theoretically be infinite, which is kind of cool as well. So I've got some code in main here, which says the first 10 terms of the Fibonacci sequence are, and then it calls this Fibonacci function here, which is this struct, and I intend to implement iterator for the Fibonacci struct here, which is Fibonacci struct will basically be our iterator, and it says take the first 10 elements of it. Note take here is defined by the iterator trait. Take, LMNOPQRST for take. And it just means like, see if we have array 1, 2, 3 here and we're iterating over it, take 2, it'll only give us the first 2 things back. So just take the first 10 things of the Fibonacci sequence. Note it even says take is often used with an infinite iterator to make it finite. So this here 0 dot dot is an infinite iterator that'll go 0, 1, 2, 3, 4, 5 up to, you know, until it overflows, I suppose. And so this will restrict it down to just the first 3 things. One of the exercises this week was almost DRY Fibonacci iterator. Oh, very cool. And so we'd like to write this thing. So the way I'm probably going to write this is I'm going to say, well, for a Fibonacci sequence, we're mostly interested in what the current element is and what the next element is, I suppose. When you want to create a new Fibonacci iterator, what are we going to instantiate these fields with? Probably we're going to start off with the first element is 1 and the next element is also 1. Yeah, that seems about right. So the first, the first two elements in the Fibonacci sequence are 1, 1, then it goes 2, 3, 5. It just adds like the previous two things together. And we can implement, don't implement Fibonacci, implement Iterator for Fibonacci, so it can be iterated over. Now again, there are two required things to implement here, and I'll just tell Rust Analyzer to sort of fill out the structure for me. So we need to tell it what does the Fibonacci iterator produce. The thing it produces are U32s, right? I defined these things here as U32s, just like numbers. There's a few different types. This could be a few different number types, but say something like string would not make sense here really, like some kind of number that it produces. And then the next function, which says you get an exclusive borrow on yourself, so you can mutate the elements in the Fibonacci struct that we have here, and we need to produce an option of an item. So how would we do that? Well, there's a couple things that an iterator really needs to do. It needs to be able to produce that item, and it needs to also sort of be able to like move on to the next step, right? So the current thing that we're going to spit out is going to be like self.current. That's what we intend to spit out of the iterator. And so we're sort of ready on that account. We might want to do some code here and then give back whatever the current thing we're talking about is. But we need to set ourselves up for success in that the next time they call the next function, these need to have moved on to sort of the next elements in the sequence. So how are we going to do that? Well, the next, self.next is probably going to want to be whatever the current value is plus itself, I suppose. Right. So how do I say this correctly? Like if this is, we start off with 1 and 1, the next element is going to be these two things added together to produce 2. So we add the two things together and that's going to be the next thing. And then the current's going to need to be whatever the next was. So I guess I'm going to just remember this for a second. Next is going to be this stuff here. We'll then say self.current is equal to, not next, self.next. So current becomes this one here. Next becomes whatever we calculated the next thing should be. And then we spit out current at the very end. There's probably a more efficient way to write this in like less lines of code. But hopefully this is like relatively clear in that this is like what our current item is. This is what the next item should be. I guess we'll call it next should be this. Then we say, now mutate ourselves such that the current thing is whatever our next one was. So that'll be what's like spit out next time. This function's called. And next is whatever next should be. Right, which is just the two things added together. So does this work? 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. So yes, it does. And then maybe we would want to use this to make some sort of like triangle and stuff. And because we implemented this as an iterator, it makes it like very easy to do something like that. We could say for line in Fibonacci, take 10, Fibonacci, take 10, dot map, whatever the Fibonacci number is into, let's say a hash times or dot repeat that number amount of times. And then this here should spit out like a nice sort of Fibonacci style triangle for us. Right, which is kind of cool. And we just sort of get all this stuff for free by doing things as an iterator, which is very nice and convenient. And very much demonstrates like the power of iterators. So anyway, that's implementing sort of like an iterator just based on its own state here. Sometimes we might want to iterate over something like a vec, right? So let's say we have a function myVecIter that we'd like to use like this. We create a vec of 1, 2, 3, 4, 5, and we call myVecIter with a borrow of the vec, and we'd like to iterate over it. If we're borrowing the vec, then the items it spits out should probably be like borrowed elements of that vector. So how might we want to do this? Well, the VecIter, myVecIter is meant to return back this VecIter struct here, and we want to implement iterator for that VecIter. So it needs to know that the vec that it's iterating across, so we're going to have to include that. let's say the vec we're iterating across is a borrow of a vec of t. Now that's immediately going to run us into two problems. What is t and what is this like, what is the lifetime of this borrow? So we'll say actually a VecIter really cares about the type that it's iterating over. And it also has this inherent lifetime tick a, which is however long the vec itself lives. So this is essentially putting in code to Rust that the VecIter must live at least as long as the vec that it's iterating over. So you can't get any scary stuff where you drop the vec, that's no longer valid memory, but we still keep iterating over it, which is definitely possible in some other languages. So we're putting that into code. Rust forced us to do that. And my VecIter should theoretically just spit back out this VecIter here, like this. Of course, naturally, we now need to say the t's here. Oh, and nicely, it's also inferred the lifetimes here for us with lifetime elision. But you can imagine that this is essentially what it's inferring here. That there is some lifetime tick a, which is the lifetime of that vec, and this lifetime in the VecIter that's, you know, that's related to it in this way here. What else? There's one other thing that a VecIter needs to know that I need to put here. Does anyone want to take a stab at what other bit of state does this VecIterator need to keep track of in order to iterate across it? There's one extra thing that we need here. So we've got the vec itself. You know, we know the vec that we are iterating over. What else do we need to know? The end, maybe? Oh, video frozen? Stream is healthy? Oh no. Maybe I hope I'm quietly hopeful it's not my end. The element we're up to is probably what I was looking for here. Yeah, the position. What element are we currently up to over the iteration? We know the end because that's the vec keeps track of that with the length, right? Vec.len. So that's sort of already included in there, which is nice for us. And I'm assuming this is sort of coming from C++, where that's very much going to be the case. Did anyone else say anything else? No, so yeah, and so we need to know which element we're currently looking at. And I'm just going to do that as a index, right? An index into the vec. And when we create the iterator, what's the index going to start off at? Probably 0. We want to start at the beginning of the vec. Now we're ready to implement iterator for VecIter, right? But naturally, what's a VecIter? I don't know what that is. Instead, it needs to be, well, impl for any lifetime tick a and any type t, iterator for a VecIter of the lifetime tick a and that type parameter t. Okay, then it needs to know the item and how to get the next thing. So what is the item going to be? Well, it's not actually going to be a t here because that implies that it's going to be able to spit out owned elements, right? It's going to, like, the item you'll get back is the t, and if we trace this t back, that's the t that's owned inside the vec. If it's a vec of strings, let's say, then that's saying that it'll spit out strings. But we only had a shared borrow access to the vec, so the best we can really do here is a shared borrow of the t. So actually the item here should be a shared borrow of a t we're going to spit out. And naturally Rust is going to go, you know, pesky Rust is going to go, what lifetime though? What lifetime is this t living for? The answer is, well, however long the vec lives for, which was tick a, which got put into the tick a here, which was the tick a there, which is the tick a here, which is the tick a here, which is the tick a there, which is the tick a here, right? This is like, I hope at this point lifetimes are starting to get to like a, oh, I get why it's all over the place here. Lifetimes are what Rust is using to track all of, like, literally to track the lifetimes of things. It goes, oh, tick a there is tick a here is tick a there is tick a here is tick a there, and it sort of tracks it all the way down into like, right, the lifetime of the item that the VecIterator will spit out traces it all the way back to is whatever the lifetime of this vec is. So no item spat out from this iterator should live longer than the vec itself, which is great. No use after freeze. That's exactly how long it should live. So that's pretty cool. Now, how do we get the next element from our vec? Well, I would say, like, let our current index be self.index, right? So this is the current index we're up to. And we're going to want to go like self.vec, you know, get me the current index. maybe we'd like to write this as a match. So get in particular takes an index and returns an option of whatever the vec holds. So I'll say match on this. If we get some item back out, then that's great news. Spit that item back out. If there is no element at all, then then we don't have an element to give back. We must have reached the end of the vec, I suppose. And so we can simply return none back as well. Right. There is one problem still left here though, which is that as we've written it, it's just going to give the 0th element, the 0th element, the 0th element every time it calls next. And so we're going to have to say self.index, plus equals 1. So remember the current index, increase it by 1 in the iterator, and then get the current index in the vec. And dong, I was hoping someone would notice this. Notices that like some item and none here, like, what's going on with this? Couldn't this just be a question mark? And it absolutely could. In fact, we could even reduce this all the way just down to this, because we return an option of the item of the vec, and vec get returns an option of the item of the vec, as which Simon notices. Yes, and so you could just use it at the end here. But you could also say something like let item equals self vec get question mark, and then give back some item here. If get gives you back none, then it'll return none to the iterator. If it returns back some, then great, we get the item back out and we can spit it out here. And you might also prefer it to be like this, because then you don't need this current index thing. Oops. You just go, get me the thing of the current index. If you get it, increase the index by 1 and give back some item. However you choose to write it is completely up to you. Maybe this is actually a little better, because although they'll behave exactly the same, the slightly weird thing is if you reach the end of the vec in this, in this way of doing things, which I had here, there's this weird thing where the iterator won't return none until it gets to this line. And so like the index will keep increasing over and over if you keep asking next, 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 even though it's just giving you back none, 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 none. And eventually if you call next, enough times on this iterator, this could overflow and panic the application. Like the index could end up overflowing, which is pretty funny. So maybe we actually do prefer to write it like, oh gosh, I've lost my history here. Maybe we do prefer to write it like let item equals self get self.index. Then we question mark this, so it returns if it doesn't find the item. Only at this point do we increment the index by 1, assuming like we actually found something, and then give the item back. Yes, Rust does check for overflows. If it overflows, by default, it'll panic. There's ways to get isn't that a huge runtime penalty? Yes and no. It kind of is, but probably less than you think. It's only by default done in debug builds. When you do a release build with optimizations, it turns off the panicking. And you can easily opt out of the panicking by saying, instead of like plus equals like this, you could say something like wrapping add, which means, wrap around on overflow. Or you could do something like a saturating add, which means if you add 1 but it can't get any bigger, just don't change the number. There's like all different kinds of behavior that you can just tell Rust to do. It's pretty flexible. But anyway, this presumably should do the right thing, and all the lifetimes and everything magically work out. And then we simply say, yeah, we have our vec 1, 2, 3, 4, 5. For item in my VecIter, if I borrow to that vec, print the item out. And there it is, 1, 2, 3, 4, 5. Ignore the Fibonacci, naturally, that's just above it. But there's that vec being printed out. Does it work for things of a completely different type? Let's say I had string from Dong, we had string from Simon, and we had string from poor Miguel, who's trying to get back on the stream. And yes, it works no matter what the type is. So that's also quite nice as well. All right, 1 minute passed. Yes, okay, that's it. That's all we wanted to talk about. As many questions as you want, spit them out here. And otherwise, naturally, of course, similarly, as many questions as you want, the course forum. But otherwise, that's all our content before Flexi Week. Yay. So enjoy your Flexi Week, everyone. Yeah, I hope you have fun playing with the assignment. Naturally, we still have our workshops tomorrow, so I might see some of you, or tomorrow and Friday, rather. So I might see some of you then. But no, not assignment week, Flexi Week. Flexibility and stuff. So no, please enjoy your flexibility weeks if you can. You'll obviously probably end up spending some of that time working on assignment 1, but try and find some time to enjoy yourself as well, naturally. But yeah, any other questions? I'll push this code up while we're waiting, but yeah, any questions I'm more than happy to chat about until you're out of questions, and we'll call it quits. Commit, lec10, push. How do we write a doc test for some functions in a trait that return nothing, just change some internal fields? We actually talked about this at the very beginning. I can't remember who asked this question at the beginning. Wait, where was it? I can't find it in the chat anymore. I think there was a point that we talked about this. But the idea was that you probably... Oh, yeah, Mitchell. There you go. So Mitchell asked for it earlier on. Oh, yeah, there it is. Yeah, now I see it. How do you write a doc test for a function that returns a unit? It might be best to just sort of scroll back to the beginning of the lecture when that question was asked. Yeah. But just as the cliff notes of it was... sometimes, like, if a function doesn't return anything, or in other words, returns a unit, there is occasionally a decent way to test it, in that you might be able to, like, observe some side effect that it creates by constructing a bit of a test for it. Sometimes that gets really complicated to do. Sometimes it just does a side effect that you can't really control, like printing or just, you know, reading, doing weird stuff that you just can't deal with. In which case, usually the suggestion is just like write it as an example. Like write your doc test as an example. The doc tester will make sure that it doesn't panic. It'll make sure it compiles. So it'll do some basic checking, but you know, write it without things like assert, eq and stuff if you just can't find a way to do it because the function is inherently quite difficult to test. So that's my vague example, my vague advice rather there. We talked about it a little more at the beginning of the lecture if you're looking for more. But yes, don't worry. We understand we understand the difficulty in it when it's a tricky situation like that, and we're not like meanies who are going to be like, wow, you didn't manage to do this. That's that's horrible. No, we understand the problems that arise in this for sure. Cool. Any other questions? I'll give till... If I don't hear a question by 45 seconds past, then I'm gonna wrap things up and turn off the stream. But any more questions at all? No problem, Dong. No, 10 more seconds. A reminder, if you do get any questions later on, whether it's about the lecture or anything else, the course forum's always open. 3, 2, 1. All right, no more questions. Thank you everyone for coming. Enjoy your flexibility week. Chat to us on the course forum if you have any questions. I'll see some of you in the lecture, in the workshops later on, tomorrow and the day after. And we'll see you in the lectures again Monday, week 7. So, see you all later. Bye for now.